All right, how's everybody doing today? So today we're going to be talking about naming ionic compounds from their formulas and writing their formulas from their name. And we've been talking about ions, positive and negative ions, cations, anions. Again, positive ions, those are pretty much the metals that lose electrons, and then the non-metals become the negative ions because they gain electrons. So again, just a little refresher, cations are positive, and these are metals that lose electrons. And again, they're losing electrons to become more stable so that their electron configuration looks like one of the noble gases. And then anions are the negative ones, and those are nonmetals that gain electrons. Again, those guys, their highest occupied energy level is close to being full, so it's easy for them to gain electrons and become negative so that their electron configuration looks like one of the noble gases. So what really happens is that electrons will transfer from something like, we'll be pretty basic to start out with, something like sodium, which has that one valence electron in the 3s orbital, and that will transfer to something like chlorine. Let me use a different color for chlorine just to make it pop like my lip gloss. So chlorine is in group 7, so it has 7 valence electrons, 2 in the 3s and 5 in the 3p. So what happens is this electron transfers from the sodium to the chlorine, leaving a sodium with an empty highest energy level. So we write it like this, and a chlorine with a full highest energy level. Because it took sodium's electron, which makes it a negative charge. Then what happens is, because oppositely charged particles attract each other, opposites attract, the sodium and chlorine, which is now chloride, stick together, and we have a sodium chloride unit, they're called, formula unit. So because sodium is a positive one and chloride is a minus one, a negative one, it just takes one of each to balance each other out, and we end up with a formula that reflects that, one sodium, one chloride. If we only need one of an element, a certain ion, then we don't need to bother writing a 1 down. We just write the formula for it, the symbol. So that's one way of showing what goes on. I'll show you a couple different ways to write formulas. I'll give you another example of this method. Something a little bit more difficult. Let's take, let's say a magnesium and pool of phosphorus. How about that? And let's use this nice dark red for the phosphorus. There we go. So magnesium is in group 2, so it has 2 valence electrons. We'll put them over here for fun. Phosphorus is in group 5. So it's got 5 valence electrons. And we'll put them like this. 2 of them are in the S sublevel, and the other 3 are in the P sublevel. Let me get rid of this. Oh, I didn't want to get rid of the whole thing. Stupid smart boards. I'll just get rid of the circle this way. There we go. So, again, electrons will transfer from the magnesium to the phosphorus. This one will go here. And this one will go here. And, well, that's all the electrons that magnesium wants to lose, but that phosphorus isn't full yet. So what do we got to do? We got to get another magnesium. It has 2 electrons. So this one will go up here. Well, now that phosphorus is full, but this magnesium has 1 more electron that it wants to get rid of. We got to get another phosphorus. So now this electron can go here. Well, now this magnesium has gotten rid of both of its electrons that it wants to get rid of, but this phosphorus over here isn't full. So we got to get another magnesium, which has 2 more electrons to get rid of. This one will go here, and this one will go here. Now, everybody's happy. All of the magnesiums have lost 2 electrons each, and both of those phosphorus atoms have gained 3 electrons each. So what that gives us then is 3 magnesiums that have emptied out their highest energy level and each become positive 2. We've got 3 of those. And 2 phosphorus ions, phosphide, that have, I switched up the colors, didn't I? That's okay. That have filled up their highest energy level by taking the magnesium, the electrons from the magnesium, and each one of them has gained 3 electrons, so it gives them an overall charge of -3. So we have magnesium, and this is now called phosphide. So it would be called magnesium phosphide. And to write its formula, we're going to use these numbers as subscripts. So Mg3P2 would be the formula for magnesium phosphide. So to name it, again, the metal, we don't change the name of that. It's just magnesium. Or like in the one before this, it just remains sodium. This compound's name was just sodium chloride. The non-metal element, it's the name, the end of its name gets changed to having an IDE on the end. So instead of phosphorus, it's phosphide. Back here, instead of chlorine, it's chloride. IDE. If we had one with oxygen, it would be oxide. With fluorine, it'd be fluoride. So on. Okay? So that is kind of how we name them, and also one way to figure out what the formula would be. Another way to figure out formulas is we know that everything in group 1 is going to lose that 1 valence electron and be a +1. Everything in group 2's got 2 valence electrons, is going to lose them and be +2. The elements in group 3, boron, aluminum, gallium, so on, those have 3 valence electrons. They're going to lose them and become plus 3s. The elements in group 4, again, tin and lead are the only ones that really form ions out of group 4. And they are metals, so they tend to lose those electrons. But they're tricky. They can either lose 2 electrons or 4 electrons. So they're either going to be plus 2 or plus 4. And after that, once we get to group 15, then the elements start to gain electrons. The atoms start to gain electrons and become negative ions. So all the elements in group 5 are negative 3s. So let me go ahead and write this stuff down instead of having you stare at a blank screen. So group 1 is plus 1, group 1, plus 1. Yeah, let's do it that way. There we go. Charge. Group 4 can be plus or minus 4. And honestly, tin and lead can be plus or minus 2, or plus 2 or plus 4. Either one, depends on the situation. We'll talk about that in a little bit. Again, the rest of the ones in group 4 tend to not form ions at all. Group 5, there were, again, the magic number is 8, and when we have 5 valence electrons, we're more than halfway there, so they'll gain 3 and become negative 3. Group 6 is negative 2, because they'll gain 2. Group 7 have 7 valence electrons, they'll gain 1 and be negative 1s. Okay? So, since we know what charges they are, we can do things like, let's say we want to make a compound out of, calcium and nitrogen. Okay? We can write the symbol for calcium with the charge that it would have. Calcium's in group 2, so it would be a plus 2. Then we write the symbol for nitrogen with the charge that it would have. It's in group 5, so it would be a negative 3. Then we do what we call the crisscross method. It'll make you want to jump. Wear your clothes backwards and all that stuff. So what happens is the 3 from the nitrogen, the negative 3, comes down here behind the calcium as its subscript. And the 2 from the calcium comes down here behind the nitrogen as its subscript. We drop the positive and negative signs. And there we have the formula. And to name it, well, again, the metal doesn't change its name at all, and the non-metal's name changes to an IDE ending. So calcium nitride. Okay. So again, that's called the crisscross method. One thing to note with the crisscross method, if we did something like calcium and oxygen, calcium's a plus 2, oxygen's a minus 2. This 2 would come down behind the calcium. This 2 would come down behind the oxygen. And now we have a 2 for each one of them. And it's kind of like math class. If they can both be divided by the same number, we do that and reduce it. I know math teachers don't like to use the word reduce anymore, but I don't care. I'm not a math teacher. So there. So both of those numbers can be divided by 2, and so we should write the formula as CaO. The plus 2 is going to balance out the -2, and you just need one of each. And of course, this would be calcium oxide. Oxygen becomes oxide. Okay. Now, we've got a special situation to talk about with the transition elements. Transition metals. Your book doesn't really go into this too much, but I'm going to anyway. With the transition metals, because they have electrons that are going into d orbitals, they can do some funny things with the number of electrons that they give up. And so they can have multiple positive charges. For example, copper can be +1 or +2. Iron can be +2 or +3. Some exceptions. Are zinc, which is always +2, cadmium, which is always +2, and silver, which is always +1. Okay, so what I'm about to talk about, we don't really need to do with these guys because they're always the same charge no matter what. But with all of the other transition elements, if they are not in groups of 1 or 2, or aluminum, I guess we'll throw aluminum into that exceptions list. Aluminum's always +3. All other metals not in groups 1 or 2 must have a Roman numeral in the name to show the charge of the metal. So, for example, we have this one, Cu2O. That's 2 coppers with 1 oxygen. The charge of the nonmetal never changes. It can never change. We'll write that down. Charge of nonmetal can never change. That'll be important pretty soon also. So, the charge of the oxygen can never change. Oxide. So if it takes 2 coppers to balance out the 1 oxygen, and we know that the oxygen is -2 because it's in group 6, then each of those coppers must be +1. So it takes 2 coppers that are each +1 to balance out the 1 oxygen, which is a -2. Okay? So, since the copper is a +1, the name is copper 1 oxide. I'll do one more of these. This one's kind of ugly, but iron with oxygen. Well, in this case, hopefully somebody in the room speaks Spanish and understands why I said this one's kind of ugly. In this case, again, the oxygen has to be -2. So if the oxygen is -2 and there's only 1 iron there to balance it out, then that iron has to be a +2. So this would be iron 2 oxide. I will do one more just to throw up the other example. This is the other ion that iron can form. So this time there are 3 oxygens. Okay? Each one is -2. That's a total of -6 then. So if we have 2 irons, and it has to have a total of +6, then they must each be +3 ions. So this would be iron 3 oxide. Any questions? Just kidding. I'm not here to answer them. Okay. I think I'll show you this real quick also. Another quick way of doing this is what I call reversing the crisscross. We talked about using the crisscross method back here to take the charges, drop them down behind the, crisscross them down behind the element symbols to figure out the subscripts. Well, you can do the same thing over here to figure out what the charge is on the metal atom. What you got to remember, though, is the charge of the nonmetal cannot change. So in the case of this one here, you would take this 2 and stick it back up here, and that would be a -2. You'd take this 3 and stick it back up here, and that would be a +3. And they'll tell you iron 3 oxide. That method breaks down a little bit right here with this other one, because this one here, there's no subscripts, which means it's a 1 each. So if you took this 1, put it back up here as a -1, and took this one back up here as a +1, well, then you've got oxygen as a -1, and it can't be. It's got to be -2. So you'd have to change this to -2, which means you'd have to change this to +2. So if you want to do the reverse crisscross method, fine, but just make sure that you're checking the charge of the negative ion to make sure it's the right one, because that cannot change. All right, we're going to talk real briefly about what's in lesson 22 for you, which is polyatomic ions. Okay? And we can break that word down, polyatomic. Poly means more than one, right? Atomic would obviously indicate atoms. And then ions. So we're talking about ions that are made of more than one atom. That's what they are. They are groups of atoms bonded together. They bond together by what are called covalent bonds. We'll talk about those more later. So groups of atoms bonded together that carry an overall charge. Okay? So with this, we're talking about things like CO3, which is called carbonate, or SO4, which is called sulfate. And carbonate, before I get too far ahead here, carbonate has an overall charge of -2. Sulfate has an overall charge of -2. All right, there's another polyatomic ion that is sulfite, which is also a -2 charge, but you notice the difference is there's one less oxygen. And so the name changes to sulfite, ITE. Most of the polyatomic ions are going to have either ATE or ITE endings. And what that does is it gives you an indication of the number of oxygens in the formula. Okay? So the main one, the main polyatomic ion made from those elements, like carbon and oxygen for this one, or sulfur and oxygen for these, the main one will end with ATE. If there's one fewer oxygens, then it's going to be ITE. If there are two fewer oxygens, then they put a prefix hypo in front of it, like hypochlorite. So it keeps the ITE ending, but you add the prefix hypo in front of it. So this would be hyposulfite, which I don't think actually exists, but you know, we can use it as an example. Anyway, you would use the charge of the polyatomic ion to write the formula, just like you would with a single ion, a single atom ion. And as far as naming them, you don't change the name of the polyatomic ion. You just leave it alone. So, and by the way, there's a chart of polyatomic ions with their formulas and charges on the back of your periodic table. So, any of these that you need to use, you can just look on the back of your periodic table, and there's a chart of them right there. So if you have something like, oh, I don't know, we'll say nickel as a +2, and, oh, bromate. Bromate sounds fun. BrO3 is bromate. It's a -1. So since bromate's a -1, it's going to take two of them to balance out the nickel. If we did the crisscross method, we would have one nickel. And since we have to have two of these BrO3s, these bromates, you have to put the formula in parentheses. And then put the two outside of the parentheses, like that. Okay? And then to name it, once again, since nickel is not in group 1 or 2, we have to put the Roman numeral there to show its charge. So nickel 2, and then BrO3 is the formula for bromate. So we just write down bromate, and that's it. Okay? There is one polyatomic ion that it has a plus charge, and that is ammonium. NH4 is ammonium. It's a +1. And let's say we put it with sulfur, sulfide, which is a -2 because it's in group 6. The 2 would come down behind the ammonium, which means we have to put it in parentheses with the 2 outside of it. And then this 1 would come down behind the sulfur, so we just need one of those. And we would have ammonium sulfide. And I'll throw up one more here just to make one more point. If we have something like calcium chromate, sounds fun. Calcium's a +2 because it's in group 2. Chromate is CrO4, and that's a -2 charge. Okay? Since this is a +2 and this is a -2, if we did the crisscross thing, they'd each be 2. And so we can reduce that to each being 1. If we only need one of the polyatomic ion, well, then we don't bother putting it in parentheses. There's no need for it. Okay? And to name this, calcium's in group 2, so we don't need a Roman numeral for it, because it's always going to be a +2. So it's calcium. And then the name of this polyatomic ion is chromate. So you just write that down. That's all there is to it. All right. I hope this helps. From here, you're going to read through lessons 21 and 22 in the book, and then answer the questions that are at the end of each section. All right. We'll see you.